This lesson is about simply supported beams. Now these are beams which are held up with two supports, and the aim of the lesson is for you to understand how to calculate the reaction force at each support, and also how to deal with uniformly distributed loads. So let's get started. What we know so far from the last lesson, working out balancing on a single pivot, is we can we can alter the loads to actually keep the thing balanced. That's exactly the same really with simply supported beams, but this time we've got two supports. And as I said earlier, the forces that hold the beam up are called the reaction forces. So we've got two reaction forces supporting a beam. Now you might use this, for example, when designing performance cars, because it's very important for the suspension, for the weight of the car to be distributed 50-50 front and back on the car. So if you're designing a racing car or something like that, you know the weight of the driver and so on, the forces from the aerofoils, you can calculate where they're going to go in the car to actually get a 50-50 weight distribution. So typically, you'll know the loads actually on the beam, and you need to calculate the force at each support in order to keep the beam steady. And what you're learning here is a procedure. The maths you'll find is very straightforward. It's the procedure that's the important thing. So what we do, just like we did last time, we take moments. But this time we take moments about each support in order to calculate the reaction force on the other support. So typically we've got two unknowns, reaction 1 and reaction 2, and normally you'd have two equations to actually solve this. But there is actually a clever way around this, which I'll show you, which avoids that and makes the whole thing a lot simpler. But it's all about following the procedure. So what we do, we take moments about one of the supports, and that effectively takes that out of the equation. So here's an example. We've got a simple support here, we've got a simple system here, and what we're going to do is to take the moments about reaction 1 to calculate the unknown force on reaction 2. And this works because the moment going through, by taking moments about the support itself, because the reaction 1 is at 0 distance from where you're taking the moments, there is no moment there, so that eliminates reaction 1. So the second thing we do is to state the principle of moments, telling us what's actually happening, and then working from the left-hand side, we work across the beam, working out which way each of the moments is pushing the beam, whether it's clockwise or anti-clockwise. So here's an example for us to work on. So when you do these problems, the first thing you do is state where you're taking your moments about. In this case, it's R1, make that very clear. I'll put a little star on there just to make it a bit easier to follow. And then state the principle of moments. Clockwise moments equals anti-clockwise moments. This is part of the procedure. Then we look at the first force, starting from the left-hand side, which is the 5 Newton force acting at 1 metre from the pivot, or from the where we're taking moments. So, and that's going to turn the beam, tend to turn the beam in an anti-clockwise direction. So that goes on the anti-clockwise side of the equation. And there it is. We go down the beam to the second load, which is the 20 Newton load. That's pushing downwards again. That will tend to turn the beam in a clockwise direction. And we know that it's 3 metres out from the pivot. Therefore, we can put in 20 times 3 on the clockwise side equals 5 times 1. We then go a bit further down the beam to get to the R2. That is pushing upwards, so that is trying to tilt the beam anti-clockwise, and that's 4 metres from the pivot point, and therefore That's also an anti-clockwise, so that goes in there. So we've now built up a little equation. All we need to do now is to simply multiply that out. 20 times 3 is 60, 5 times 1 is 5. Therefore, you get this little equation at the bottom here. 60 minus 5 divided by 4 gives us 13.75 newtons. Now we take reactions from the other end. This time we're taking from R2 to find R1. So again, make it really clear what you're doing. Put down the statements here, and then we start again. So that's where I'm pivoting about there. That's where I'm taking my moments from. I start at the left-hand end. The 5 Newton load is pushing down. That will still tend to tilt the beam in an anti-clockwise direction. So that goes on to the anti-clockwise side of the equation. Reaction 1 is pushing the opposite way. That would tend to turn the beam in a clockwise direction. So that goes over here. And then the 20 Newton load is also trying to turn the beam in an anti-clockwise direction. So that goes on to there. Multiply it all through, rearrange the equation, and you get R1 is 11.25 newtons. Now you can double check these because you know the force, the sum of the forces pushing down should equal the sum on the forces pushing up. And we know we've got 25 newtons pushing down. If we add up the loads, the two reaction loads, we've also got 25 newtons as well. So you know you've got the right answer there. And as you would expect, the reaction force at reaction 2, where it's got more load on, is higher than the reaction force on 1. So here we have a typical system for you to have a go at. Remember, it's procedure you're following. Be methodical about it. State where you're taking your moments from, and also state the principle of moments as well. Just step through it and you should get the right answer. If you get stuck on it, no problem. I'll go through it a little bit later on. Pause the video now. So the answers you should have got are for R1 25 newtons and for R2 100 newtons. If that's what you got, well done. If you didn't get that, let's go through it. So the first thing you need to do is to state where you're taking your moments from. Taking moments about R1 to find R2, and then clockwise moments equals anti-clockwise moments. So first, then I next need to put a star just to remind me. I'm taking moments about R1, so I'm going to start here and work from left to right. So the first one I come to is the 75 Newton load, and that is pushing down like that in a clockwise direction. It's 2 meters out, so it's 75 times 2 on the clockwise side. The next one I come to is R2, and that is pushing that way, which will tend to tilt the beam in an anti-clockwise direction. Push the beam in an anti-clockwise direction. That's 5 meters out, so it's R2 times 5 plus this one here is pushing down that way. So again, that's going to tilt the beam in a clockwise direction. It's 7 meters out, so therefore it's 50 times 7. Then all you need to do is to multiply them all out. So you get 350 plus 150 equals 5R2. Therefore, R2 equals 500 over 5, which equals 100 newtons. Then we do the same thing for R2. So let's put a line down here to make it nice and clear. So taking moments about R2 this time to find R1. Then state the principle of moments. Then we start off from here, again going left to right. So first one we come to, just cross those out, is R1, and that's going to be pushing the beam that way in a clockwise direction. So on this side we say R1 times 5, and then we come along here. This one's going to be pushing down that way in an anti-clockwise direction. So that's 75 times 3 on the anti-clockwise side. And then this last one, we're pivoting about here. This last one, 50, is going to be pushing down that way again. That's going to be pivoting down like that. And that is going to go in an a clockwise direction as well. So that's 2 meters out, so that's 50 times 2 plus that one there. Multiply it all out. R1 equals 225 minus 100 divided by 5, which equals 25 newtons. And with 25 plus 100 equals 75 plus 50. Then you know you've got the right answer. Okay, so uniformly distributed loads. Now, so far we've only considered point loads on the beam. We consider the load to acting on a particular point on the beam. And often we need to consider UDLs, uniformly distributed loads, which is a load distributed along the length of the beam. Now, in some situations that could be, for example, the weight of the beam itself, or it could be, for example, if you've got a vehicle, a uniformly distributed load in the load area of the vehicle. Normally, it's shown with a series of semicircular bumps, as you've got shown in the diagram here. That's a uniformly distributed load, and it's given a load per metre. So in this example here, we've got 15 newtons per metre over 3 metres. Therefore, the total load must be 45 newtons, and we can consider it acting in the centre of the uniformly distributed load. In this case, the UDL is spread over 3 metres. Therefore, we consider it the same as 45 newtons acting 1.5 metres away from the pivot. And that's all you need to do with UDLs. Convert them into a single point load with the point of the load acting about the centre line of the UDL and treat it as a point load. So here we have another question, and this time calculate the reaction force again at each support. We've got a UDL this time to put in the equation as well. So if you can calculate R1 and R2, that'd be absolutely great. So pause the video now. And the answers you should have got for these are for R1, 8.5 newtons, and for R2, 16 newtons. If you got those correct, well done. Go on to the next question. If not, I'll go through it here. So here we are again. This is practice questions 2. And again, we need to calculate the reaction force at each end. This time, we've got a UDL to take into consideration, a uniformly distributed load. So the first thing to do is we can convert the UDL, so that's 7 Newton meters over 3 meters. So newtons per meter times 3 meters equals 21 newtons. And because we know that the UDL is considered to act in the centre of it, you know your UDL effectively is going to come in here. So effectively, that's 21 newtons there. And you can then ignore that there because you converted that into a single point load of 21 newtons there. So in fact, it's quite straightforward after this. So make it very clear, we're going to take moments about R1. So put a big star there. So take moments about R1. Take moments about R1 to find R2, and then clockwise moments equals anti-clockwise moments. Makes it clear to you what you're doing. And then we can say then start along. So we start along here taking moments about this point here. This one here is going to push down there like that. So that is going to be an anti-clockwise moment. So 3.5 times 1. Along here, this one here is 1.5 meters in from there. 1.5. Therefore, this one is acting in a clockwise direction. So it goes on this side of the equation, 21 times 5.5. And then the reaction force here is pushing this way, which is going to be anti-clockwise. So that will be, and the distance there is 7, so that'll be 7r2. Therefore, r2, it comes out, quite easy to work out, it comes out at 16 newtons. So it's that times that minus that times that divided by 7 gives you 16 newtons. Then take moments about R2 to find R1. So we're going from here now. Ignore that. So taking moments about here, we can then say clockwise, we'll say clockwise and anti-clockwise. So from here, this one here is going to act in again in an anti-clockwise direction. So 3.5 times 8. So it's anti-clockwise, 3.5 times 8. R1, which we're trying to find out, is pushing the other way, which is clockwise. So that is 7 R1. That's trying to push the beam that way, clockwise. And this one is trying to push the beam down anti-clockwise. So that is 721, 1 times 1.5. So therefore R1 equals 28 plus 31.5 divided by 7 comes out 8.5 newtons. And you can double check that. You know the total load is 21 plus 3.5, so it's 24.5 newtons. 16 plus 8.5 comes to 24.5 newtons. So you're pretty confident you've got the right answer because the forces acting downwards equal the two forces acting upwards. So here's the final question. Slightly more elaborate. It looks a bit more frightening to start off with. But this one, you've got to calculate the reaction force on each pair of wheels. And you're told the load in the back can be considered to be centrally located over the rear axle. So you've got a load here of 2 kilonewtons per metre over a distance of 4 metres, and that is acting directly over the axle, over that point there. So have a go at this question, see how you get on, and if not, we'll have a look at it in a minute. So if you'd like to pause the video now. Okay, the answers you should have got are for reaction 1 on the front wheels, 5.6 kilonewtons, and reaction 2, or the rear reaction, on the rear wheels, 12.4 kilonewtons. If you got that, well done. Please go on to the practice questions, the exercise questions, which are on a separate sheet. If you want me to go through it, that's no problem. Just stay on the video. So here we have practice questions 3. It's a bit of a diagram. It makes it look more complicated, but actually, if you're methodical about it and break it down, it all comes out to be quite straightforward. So what we've got to do is to calculate the reaction force on each pair of wheels. So the reaction force there and the reaction force there. And it says the load in the back can be considered centrally located over the rear axle. So it's a uniformly distributed load over 4 metres, and it's actually the middle of the load is considered to be right over the axle there. So we can say for UDL, it's going to be 2 kilonewtons per metre over 4 metres times 4 equals 8 kilonewtons. We'll keep all the calculations in kilonewtons on this particular one. And we want to find the reaction force at each end. We'll call this reaction force rear, and then we'll call this reaction force front. So we make a statement to say what we're going to be doing. We'll say taking moments about RF to find RR. So take moments then state the principle of moments, so clockwise moments. Clockwise moments equals anti-clockwise moments, and then working from right to left, we're starting at this point here, we're going to work from this side across to this side here. So taking moments about here, so this force here, if we're pivoting there, is going to push down. That will try and turn in a clockwise direction, so that's 2.5 times 1, so that's on the clockwise side, 2.5 times 1. The next one here, which is in the middle of the vehicle, again, pivoting about there, that's going to push in a clockwise direction. So that's 7.5 times 3.5. And then the other load we've got is the UDL, which we now know is considered at 8 kilonewtons. And that's over the rear axle, so that's 8 kilonewtons, and that is 7.5 metres from there. So that again is pushing in a clockwise direction. So we've got here 8 times 6.5, 6.5, that's 6.5 there, 8 times 6.5. The only anti-clockwise moment on this is the reaction force here pushing upwards, and that distance there is 6.5 as well. So that's going to be R2 times 6.5. Then all you've got to do is to put the numbers in, rearrange the equation. R2 equals 80.75 divided by 6.5, which comes out at 12.4 kilonewtons. So the reaction force there is 12.4 kilonewtons pushing up to counteract all of these here. Then we take moments about RR, take moments here to work out the reaction force here. So we state that here. Should be RR there. So for starting from here, we've got this one here. Now this is pushing here, so that's anti-clockwise. So anti-clockwise, and that is going to be 2.5 plus 3. Be careful here. 2.5 plus 3, so that's 5.5 equals 2.5 times 5.5 plus this one here. Again, it's also acting anti-clockwise, so that's 7.5 times 3. So that one there, and then this force here, because the UDL is actually acting through the pivot, we actually can ignore that because there's no moment there, because actually the distance is 0 from the pivot because it's acting in a straight line there. Therefore, the only other force is the reaction force here, which is anti-clockwise, which is R1 times 6.5. So therefore, I've put a line down here, therefore R1 equals 36.25 divided by 6.5 comes in at 5.6 kilonewtons. Therefore, double check that, you should find 12.4 plus 5.6
comes to 20 newtons, 18 newtons, and kilonewtons rather, and this comes here to 18 kilonewtons as well. So again, you're pretty sure you've got the right answer.
So, well done for getting to the end of the lesson. Remember, with simply supported beams, it's the procedure that you need to learn. The procedure is the thing you'll be marked on in the exam. Even if you get the answer wrong at the end of the day, if you followed the correct procedure, you'll get most of the marks for the question. In an exam, it's unlikely you'll be asked to calculate the reaction force at both ends. It'll be one end or the other. I show you how to do it from both ends because if you do have time at the end of the exam, it's quite useful to go and calculate the reaction force at the other end, add them up and make sure they add up to the total forces pushing down. That way you know you've probably got the answer right, or certainly got the answer right in the exam. Now, following this, there are 2 sheets of exercise questions which you should have a hard copy of. If not, they're on the screen. They have the answers there so you can self-check your own work. And if you get the answers right, then you've pretty much got this topic nailed. Well done.